Discrete probability distributions. Let's continue our discussion of probability distributions by talking about binomial probability distributions. So let's define that. A binomial probability distribution results from a procedure that meets all of these following 4 requirements. The procedure has a fixed number of trials. Each trial must be independent of one another. Each trial must have one of 2 possible outcomes. That's where the binomial part comes in. There are only 2 outcomes that are possible. And the probability of success is the same for each trial. So let's look at a couple of examples so you get a feel for this. The random variable, by the way, for the binomial distribution records the number of successes. So here's what I mean by that. Let's say that we have the following situation. In a drug trial, 800 subjects are treated with Lipitor. Doctors record a yes if the subject gets a headache within 24 hours and no if they don't. Based on Lipitor's claims, there is a 10% chance that someone will get a headache after using the drug. Does this result in a binomial probability distribution? So let's look at each of the 4 things. Is there a fixed number of trials? Yes. The number of trials is 800. There's a fixed number. Are the trials independent of each other? Yes, if somebody gets a headache, the next person may or may not get a headache. They have no effect on one another, so the trials are independent. Each trial has one of only 2 possible outcomes. You either get a headache or you do not get a headache. There are only 2 possible outcomes. And the probability of success is the same in each trial. According to Lipitor, there is a 10% probability of a success. What a terrible success of getting a headache. A 10% chance of a success of getting a headache in each trial. Brings me to one quick thing. Don't think that the word success in statistics is always a good thing like it is in life. A success is just, did the random variable achieve what you wanted it to? So let's go to the next example. Does this result in a binomial distribution? Same idea, but giving 800 subjects a dose of Lipitor and asking them how they feel. Well, the trials are fixed number. There are still 800 of them. They're independent. Assumedly, how somebody feels is independent of how the next person will feel. Each trial has one of 2 possible outcomes. Well, there are lots of different ways that people might describe how they feel, so this would mean that this is not a binomial distribution. There are far more than 2 possible outcomes. And let's do one last one. Does this result in a binomial distribution? Treating 152 couples with a fertility treatment and recording whether they have a boy or a girl. So for starters, a fixed number of trials, yes, 152 couples. The trials are independent of each other. If one couple has a girl, the next couple could have a girl or a boy, so they're independent. There are one of 2 possible outcomes, a boy or a girl. And the probability of success is the same in each trial. So this is a binomial distribution. Let's do some math for the binomial probability of a binomial distribution. So let me break this formula down a little bit for you. I apologize for how long it is, or for how complicated looking it is. P of x means the probability of x successes in the trial. So P of x, x is the number of successes. Now that exclamation point you see is a factorial, and a factorial means multiply all the numbers from that number back down to 1. So I'll show you that in some examples, but let me break apart what n and x and q and p mean in this first, and then we'll worry about the exclamation points in the next slide. So n is the number of trials. Remember the problem we were just talking about with Lipitor? That would be 800. N would be 800 there. The number of successes would be x. So in the Lipitor example, if you were finding the probability that of the 800 people, 70 had headaches, 70 would be your number of successes, 70 would be your X. P is the probability of success in one trial. So again, in the Lipitor example, that would be 10%. There's a 10% chance that somebody would get a headache, which is a sad success, in one trial. And finally, Q is the probability of a failure. Q is equal to 1 minus P, 1 minus the successes. So if P is 0.10 or 10%, Q is 90%, 1 minus 0.10. So make sure you have that formula written down. Let's do an example. Okay, there's the formula, in case you didn't get it written down before. Let's find the probability of getting exactly 3 heads when you flip 5 quarters. Okay, let's break this apart. So 3 is the number of successes. So we're finding P of 3 is the probability of 3 successes. 5 is the number of trials. So plugging in n equals 5 and x equals 3, we have 5 factorial divided by 5 minus 3 factorial times 3 factorial. Now the probability of getting a head or a tails when you're flipping a coin is 0.5. So the probability of a success or a head here is 0.5. That's our p-value, 0.5. And the probability of a failure is also 0.5. So our q-value is also 0.5. So we have 0.5 to the third times 0.5 to the 5 minus 3, which will be a 2. Okay, here's the factorial. If you haven't seen factorials before, 5 factorial means 5 times all the other whole numbers back down to 1. So it means 5 times 4 times 3 times 2 times 1. And 3 factorial means 3 times 2 times 1. Now when you're doing the parentheses, 5 minus 3 factorial, don't forget order of operations and do the inside first. Do your parentheses first. So 5 minus 3 is 2, and 2 factorial is 2 times 1. And then with the calculator on the right-hand side, 0.5 to the third power is 1.125, and 0.5 to the 2 power is 0.25. If you don't have a good calculator with you, or you're not using a graphing calculator that can do binomial distributions, start reducing to make your numbers a little bit nicer. So notice we have a 3 in the top and the 3 in the bottom of our fraction, and same with the 2's. So we get 20 over 2 for the fraction, and then 0.125 times 0.25 is 0.03125. So we have a probability of 0.3125 is the probability of getting exactly 3 heads when you flip 5 quarters. Okay, I want to go through an example that ties in the last lesson to this current lesson. So let's say that an exam consists of multiple choice questions, and they each have 4 possible answers, one of which is correct. Assuming that you guess to 6 of these questions. In the last lesson, we found the probability that none are correct. So the probability that none are correct, if you have 4 possible answers, you have a 0.75 chance that you're wrong, that none are correct. With 6 questions, so 0.75 to the 6 is 0.178. Now the probability that at least 1 is correct is 1 minus the probability that none are correct. Again, that's what we talked about in the last lesson. So that would be 1 minus 0.178 or 0.822. And then finally, find the probability that exactly 4 are correct. Well, we have a binomial distribution here. We have right or wrong, So correct or incorrect. We have a fixed number of trials. We have 6. Everything has an equal chance of being correct if you're guessing. So and they're independent of each other. So we can use that nasty formula from before. So 4 correct would be 4 successes. X is equal to 4. So the probability of 4 successes, and 6 is the number of trials. So n is equal to 6. So plugging n equals 6 and x equals 4 into the first part of our probability formula gives us 6 factorial over 6 minus 4 factorial times 4 factorial. The chance for success, the chance for randomly picking 1 out of 4 possible answers correctly, is 0.25. So 0.25 to the 4th times the probability of a failure, which is 0.75, or 1 minus 0.25, to n minus x, to 6 minus 4. So that probability that 4 are correct is 0.0329. Okay, another example. In the US, 40% of the population have brown eyes. If you randomly pick 14 people, what is the probability that 12 of them have brown eyes? So it looks like our probability of success is 0.40. That would be our P. That means that Q is 0.60. 14 people is the N, the number of trials, or the number of people we selected. And we're supposed to find the probability that 12 have brown eyes. So the probability of 12 successes. So X is equal to 12. So the probability of 12 successes is 14 factorial over 14 minus 12 factorial times 12 factorial times 0.4 to the 12th and 0.6 to the 14 minus 12, giving us 0.0006. Okay, what is the probability that at least 12 people of the 14 you picked have brown eyes? So at least means 12 or more people have brown eyes. So 12 or 13 or 14 have brown eyes. We already figured out the probability of 12 people. So if we use the same process and find the probability that 13 people have brown eyes, we would get 0.00005. And the probability that all 14 of the randomly picked individuals have brown eyes, is 0.000003. To find the probability that at least 12 of the 14 have brown eyes, we would add the probability of 12 plus the probability of 13 plus the probability of 14, and we'd get 0.000653. A quick note, because it pops up, 0 factorial doesn't actually make sense, because factorial, remember, was multiply all the numbers from that number down to the number 1. 0 factorial is already behind 1, so 0 factorial is defined to just be 1. So when we're figuring out that final probability, the 14 minus 14 factorial in the denominator, that just turned into 1. I won't go through this whole thing, but I did want to show you how you would create your own probability distribution for rolling a die 5 times and counting up the number of 3s. So in the last lesson, when we just introduced probability distributions, we took a look at charts that looked like this, where we had X as the random variable and it's all of its possible values, and then we gave the probabilities already, and we decided whether they were probability distributions or not. You can create your own probability distribution by using the formula for the binomial distribution and coming up with all of those possible probabilities, just like we did in the previous example with the probability of getting 12 people out of 14 who had brown eyes, or 13 people out of 14 who have brown eyes, and so on. And if you look at your probability distribution here, If you add up all of the probabilities in the right-hand column, you should get 1.